Hi, my name is Claire Xiao, and this is Physics 2212 Lab 5, Magnetic Braking with Faraday. Just as an introduction to Lab 5, the purpose of this lab is to do the following. Explore Faraday's law by observing the interaction between a falling magnet and a tube of aluminum foil. Collect observational data of a magnet falling through a conductive tube of aluminum foil. Model the magnet/tube interaction computationally, and compare your computational predictions with your observed data. My conclusion of my lab results were that the model results showed it took 1.655 seconds for the bar magnet to fall through the aluminum tube, and the experimental results was an average of 5 trials was 1.386 seconds. Next is the physics principles used in this lab. First, it was Faraday's law, which is a changing magnetic field can induce a current in its surrounding objects, and the equations are shown below. Next is the Biot-Savart law. Then Lenz's law, which is that an induced current flows in the directions where the magnetic field produced opposes the change in flux. And finally, Newton's laws, which is that force is equal to mass times acceleration, and that every action has an equal and opposite reaction. So the experimental method was first you measured the north end of the bar magnet using a magnometer on my mobile device. Then you held the tube of aluminum foil vertically while placing the magnet right above the opening of the roll. And while recording with the entire aluminum foil tube in view, drop the bar magnet through the tube 5 times. And each of these times you observed and recorded the videos to measure the amount of time taken for the bar magnet to fall through the aluminum foil tube. And finally, calculated the average time it takes for the bar magnet to fall through the length of the tube. And you do this by looking at when the magnet left the tube and when the magnet entered the tube from those videos. So the experimental result, as you can see, the 5 different trials and the time it took to fall through the tube, the average was about 1.385 seconds as shown previously in this PowerPoint. The aluminum foil tube had a length of 0.3 meters and the bar magnet had a mass of 0.023 kilograms. So this is the computational model results. The photos on the left shows the computational model of the tube and the bar magnet from 2 different angles. And on the right, it's the velocity versus time graph. And as you can see, the computational result is 1.655 seconds. So here's the code for the computational model. As you can see, a lot of this was given in the starter code. And there's certain areas where the code was edited. Step 2 was editing to create a function to calculate the magnetic field of the bar magnet, and this was from the Lab 3 code previously. And in step 1, you edit the 3 lines to match your experiment, and as you can see, the length, width, and inner radius were all entered based off of the tube aluminum foil that I was using. Next is continuing on to show more of the code in the computational model. You can see the calculation for the flux in that function, and on the right you can see the different calculations for the current and the force on the magnet, and the link to my GlowScript code is in the bottom right. Next, moving on, interpreting the simulation. The intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to clockwise current and which counterclockwise? How can you know? So the red indicates counterclockwise current and the blue indicates clockwise current. This induced current causes a magnetic field that opposes the change in flux. What happens to the dynamics of the system when you flip the magnet around? So the current would go in the opposite direction clockwise, so it would be shown as blue. How does the total time in tube of your real world system compare to that of your computational system? How might the computational system be made more accurate? So the total time in tube of the real world system is less than that of the computational system. The computational system could have made more accurate by measuring the width of the tube more precisely and remeasuring the value of mu that was transferred over from Lab 3 for the bar magnet. Another way to make the computational system more accurate would be to account for the cardboard inside the aluminum tube that reduces the effect of the magnetic field, because right now in the computational model it is calculated as being fully aluminum. And finally, what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So the velocity remains the same the entire time that it's in the aluminum tube. This shows that the bar magnet is experiencing no acceleration, indicating that the net force acting on the magnet is equal to 0 while it's in the aluminum tube. And before entering and after exiting the tube, the bar magnet experiences increasing velocity in the negative y direction. This indicates that the force of gravity is greater than the magnetic force on the bar magnet when the magnet is not inside the tube. So the lab report questions that were included for this lab: what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So the current would be larger, thus making the magnetic force larger, because resistivity and current have an inversely proportional relationship. And because the magnetic force would be larger, the magnet would fall slower through the aluminum tube. And finally, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnetic force would be weaker due to the inconsistencies in the aluminum foil in the tube, thus reducing the number of rings in the tube. And because of a weaker magnetic force, the magnet would fall quicker through the tube.